Hello and welcome to this revision session for Paper 2 for GCSE Physics in the Combined Science specification. So if we learn in this particular revision session, we should be looking at answering examination questions for GCSE Physics Paper 2 for Combined Science. So we should be able to answer our GCSE Physics examination style questions, assess our understanding on GCSE Physics and understand what topics we need to improve upon for GCSE Physics. So how should you be preparing for this revision session? Well, when completing your work in this revision session, divide your piece of paper into two sections. Make the section on the left hand side larger than the right hand side. In this left hand side section, write down your working out and answers to the questions in the revision session. When you're doing this, make sure you write in full sentences and show your full working out. Whilst in the right hand side, write down any piece of information which you find useful or any hints and tips on answering questions from this revision session. And at the end of the revision session, write up these notes into a revision sheet for you to use independently. So let's now have a look at a few questions for GCSE Combined Science Physics Paper 2. Let's start with our topic of forces. So the first question says a student ran a 100-meter race. Figure 11 shows the distance time graph for the student. The student reaches a constant speed at 4.4 seconds. Determine the constant speed of the student after 4.4 seconds. So pause the video now, then unpause the video when you want to go through your answer. Alright, in these types of questions it's very important you understand what a distance time graph can show you. Now you should be aware that the gradient of a distance time graph is the speed of the object. So what you need to do is work out the gradient of the straight line section of your line of best fit. So you would what you would do is you'd work out your gradient, which is the change in y over the change in x for the straight line section, make your gradient triangle as big as possible, and you should get an answer of 9.5. The next question says, as the speed of the student increased, the air resistance acting on the student increased. Explain why the student reached a constant speed. Use the ideas about forces in your answer. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? Well, you've got to understand what we know about the size of forces at a constant speed. Now, Newton's first and second law indicates that a resultant force causes a change in speed. So this indicates to us that there must be no resultant force acting on the object. So we can say that air resistance always acts in the opposite direction to the motion of the student. So therefore, it tells us that air resistance will increase in size until the forward force equals the air resistance force. So overall the two forces cancel each other out and the resultant force is 0, so therefore you have constant speed. The next question says another student in the race decelerates from a maximum speed of 9.6 meters per second to stop in a distance of 25 meters. The mass of the student is 75 kilograms. Calculate the average resultant force on the student. Give your answer to two significant figures. So pause the video now, then unpause the video when you want to go through your answer. Right, with this particular question, it's worth 6 marks. So this indicates to us we're going to need to use two equations, because it's a 6-mark question, we will need multiple equations. Now you think to yourself, you've got the maximum speed or velocity, you've got the mass of the student, so you can then work out the kinetic energy. So we can say firstly that the kinetic energy is equal to a half times by mass times by velocity squared. And it's always important in equations you put the numbers in first before you do any calculations and write it down. So you get then an answer of 3,456 joules for the kinetic energy store. Now you've got to think about that if the student is decelerating, they're going to lose this kinetic energy from that store, so therefore the work done, the change in energy, is going to equal the kinetic energy store. Now we also know from another equation that work done is equal to the force times by the distance moved by the object, and we're given the distance moved and we'll want to work out the force. So once again we're going to have to substitute our values in first. So we say 3,456 is equal to force times by 25. We rearrange it next to then make F force the subject, so it's 3,456 over 25, and we get an answer of 138.24 newtons. But the question asks us to go to two significant figures. First significant figure is 1, second one is 3, the third one is 8. So that's going to cause us to, when we go to two sig figs, to round up that previous value. So our answer is 140 newtons. The next question says, conservation of momentum can be used to understand what happens during collisions. Momentum is a vector quantity. Explain the difference between a vector quantity and a scalar quantity, and describe what is meant by the conservation of momentum. So pause the video now, then unpause the video when you want to go through your answer. Right, in these types of questions, it's just about memorizing the different definitions. So the first thing you need to know is the definition of a vector and the definition of a scalar. Now, vectors are quantities of a magnitude, a number, a size, and a direction, but scalars only have a magnitude, size, or number associated with them. Now, the conservation of momentum is just a rule of physics you've got to learn, and that is, in a closed system, so that's a system where energy can't get in, energy can't get out, or that there's no external forces acting on the object, the total momentum of all the objects in the system before is equal to the total momentum of all the objects in the system afterwards. That is just a fact you've got to learn. The next question says, figure 10 shows two people ice skating. Person A collides with person B, and after the collision they move together with the same velocity. Calculate the mass of person B. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this question? Well, this is the idea. It's a collision, so therefore we're going to have to use the conservation of momentum. Now, momentum is equal to mass times velocity. So what we've got to do is work out the momentum before, and it must equal the momentum afterwards. So before, it's going to be momentum is mass times velocity. So A before is 60 times by 5.5, and B before is going to be B, the mass, times by 2. And we can say afterwards that it's going to be A and B together, so it's going to be the two masses added up, so 60 plus m is equal to 4. So we can therefore work these things out. So you can see straight away that it's going to be 330, because that's the momentum of A, plus 2 times by m. The velocity of person B times by their mass is then equal to 4, which is the velocity that the two have together, times by 60 plus m. What we can then do is we can then rearrange our equation to put the m's on all of one side. So we can say 330 minus 240 is equal to 4 times by m minus 2 times by m. So therefore 330 minus 240 is equal to 90, and 4m minus 2m is equal to 2m. So therefore we can say 90 is equal to 2m, so therefore m is equal to 45. Now you've got to think to yourself when you write an answer out in physics, is this answer sensible? In 45 kilograms for a human is sensible, so it's likely to be the right answer. The next question says, figure 11 shows the free body diagram for a skydiver before and after her parachute opened. Figure 12 shows the velocity time graph for the skydiver. The skydiver left the plane at 0 seconds, opened her parachute at 80 seconds and landed on the ground at 120 seconds. What does the area under the graph represent, and explain why the velocity of the skydiver changed between A and C on figure 12. Your answer should refer to the forces on the skydiver. So pause the video now, then unpause the video when you want to go through your answer. Right, in this question you've got to understand what the area under the line means for a velocity time graph, and the area under the graph of a velocity time graph is the distance travelled, which in this case is going to be the height from which the skydiver jumped from. Now you've then got to talk about A, B and C in terms of the velocity changing and what those forces are. So let's address each point. At A, there's going to be a resultant force downwards, because when you first jumped out of the plane, okay, you know for a fact that there's going to be weight acting down, and because you haven't really got going yet, air resistance is going to be very small, so therefore the weight is going to have a greater value than the air resistance, so there's a resultant force downwards. That will cause the velocity to increase, because a resultant force causes acceleration in the direction of the resultant force, so it's going to accelerate downwards. But as it accelerates downwards, more air particles are hitting off the object every single second. So therefore the air resistance increases as the velocity increases. So the difference between the air resistance and weight gets smaller, so the resultant force is smaller, so therefore the acceleration is going to get smaller. So the acceleration is going to decrease, and then that's happening at point B. Then at C, what do we know? Well, at C, the velocity is staying the same. This indicates that there's no acceleration, so there must be no resultant force. So at that point, the air resistance acting upwards is equal to the weight acting downwards, so therefore there's no resultant force. We have reached terminal velocity. The next question says, forces are vector quantities. What is the difference between a vector and a scalar quantity? Figure 4 represents a wooden block being pulled across a surface at a constant speed in a straight line. The block is in contact with the surface. The arrow of figure 4 represents the tension force in the string pulling the block. Complete figure 4 to show the 3 other forces acting on the block. So pause the video now, then unpause the video when you want to go through your answer. Right, once again, you've just got to learn what a vector and a scalar quantity is. So scalars are quantities with a magnitude or size or value only, whilst vectors are quantities with a magnitude, value, size and a direction. Now the next question is drawing the free body diagram. Now once again, remember what we're going to do with a free body diagram is arrows represent the direction of the force by the direction of the arrow. They represent the size of the force with the length of the arrow, and they represent what the force is with the name labeling the arrow. So we should know that there should be an arrow pointed vertically downwards in the middle of the block at the center of mass, which is the weight. An arrow pointing left along the surface labeled friction, and it's going to be between the block and the carpet because it's a contact force. Another arrow pointing left touching the block in the air labelled air resistance, because that's where air will act. The air resistance will act where the air is. And then finally an arrow pointing vertically upwards from the bottom surface of the block labelled the contact force. Now this is going to be at the bottom surface of the block because it's caused by the object touching the bottom surface. The next question says, figure 5 is drawn to scale. The scale is 1 centimetre to 0.5 newtons. Determine the horizontal and vertical components of the tension in the string. Show these components on figure 5. So pause the video now, unpause the video when you want to go through your answer. Right, you've got to remember in scale diagrams that you can work out the horizontal and vertical components of a force by completing a right angle triangle with that force being the hypotenuse of your right angle triangle. So what you should be doing is you should be drawing a vertical line at the end of the tension force downwards till it meets the dashed line, and then a horizontal line along the dashed line until it meets that line coming down from that vertical force. You then get your ruler and you measure the length of each one, and then you use your scale factor of 1 centimetre equals 0.5 newtons to convert those values back into newtons to get an answer for the horizontal component to be 26 newtons and the vertical component to be 1.7 newtons. The next question says, figure 5 shows a cyclist on a straight level road. The cyclist's initial speed is 0. The cyclist pushes on the pedal so there's a constant forward force on the bike. The force of air resistance increases as speed increases. Explain why the speed of the cyclist reaches a maximum value. So pause the video now, then unpause the video when you want to go through your answer. Right, it's important to note that if the speed is reaching a maximum value, there's no more acceleration. So what happens for that? Well, you've got to know Newton's first law of motion, that a resultant force causes acceleration. So there's no acceleration, there's no resultant force. And why is that? Because the air resistance backwards is equal to the forward force going forwards, as shown on the diagram. The next question says, the cyclist accelerates from 1 metre per second to 5 metres per second with an acceleration of 1.6 metres per second. Calculate the distance travelled during this acceleration. And then in 2019, a cyclist broke a land speed record by cycling at a speed of 296 kilometers per hour. Calculate the speed of the cyclist in metres per second. So pause the video now, then unpause the video when you want to go through your answer. Right, in this question, this first one, you've got the starting speed of 1, you've got the final speed of 5, you've got the acceleration of 1.6, and you want to work out what the distance travelled is. So what equation can we use? Well, we know that v squared minus u squared equals 2as, where v is the final velocity, u is the starting velocity, A is the acceleration and S is the distance travelled, or technically the displacement, but it's the same in this particular question. So the first thing you do is sub your numbers into your equation. 5 squared minus 1 squared equals 2 times by 1.6 times by S. Simplify both sides, so 5 squared minus 1 squared is equal to 24. 2 times by 1.6 is equal to 3.2, so 24 equals 3.2 times by S, the distance, so S equals 24 divided by 3.2, which is 7.5 meters. Now the next question is asking you to convert from kilometers per hour into meters per second. So you just got to break this up into two particular sections. Convert from kilometers into meters and convert from hours into seconds. So the first thing we'll do is we'll convert kilometers into kilometers to meters. So 296 kilometers times by 1,000 is equal to 296,000 meters. Now we're going from 1 hour to seconds, so there's 3,600 seconds in an hour, 60 times by 60. So that's our new time. So we can convert it by saying it's 296,000 meters divided by 3,600 seconds is equal to 82 meters per second. The next question says, figure 9 shows a plan view of the route a car travelled from town P to town Q. The distance the car travelled is a scalar quantity. The displacement of the car is a vector quantity. Describe what is meant by a scalar quantity and a vector quantity. Determine the displacement of the car when the car has travelled from town P to town Q. So pause the video now, then unpause the video when you want to go through your answer. Right, again, it's a very common question to know the difference between a scalar and a vector. A scalar is a quantity of magnitude only, and a vector is a quantity of magnitude and a direction. Now in this question you can use your diagram to work out the displacement. So you draw a straight line from town P to town Q, because the displacement is the straight line distance from the start of the journey to the end of the journey. You can then use the scale on the diagram where 1 centimetre represents 10 kilometres by working out your length to be 5.2 centimetres, so you get 52 kilometers in your displacement. Now the direction, you would use a protractor and you would measure the angle in the difference between P and Q, and you see it's about 135 degrees. The next question says, at town Q, the car collided with a stationary van. Figure 10 shows the two vehicles before and after the collision. The total momentum was conserved in the collision. Calculate the speed v of the van after the collision. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this question? Well, you've got to say the total momentum before equals the total momentum afterwards. So let's write our equation for the total momentum before. Well, the total momentum before is going to be the speed of the car, okay, which we know is 5 times by the mass of the car, which in the question it tells us is 1,250. So we do 1,250 times by 5 plus the speed of the van, which is 0, times by the mass of the van, which is 3,000 kilograms. So we do 1,250 times by 5 plus 3,000 times by 0, which is 0, is equal to the values afterwards. So what's the speed of the car afterwards? 0.5. So do 1,250, the mass of the car, times by the velocity, 0.5, plus the speed of the van, which you know is v, times by the mass of the van, which is 3,000. So we can therefore equate them and simplify it. So we can say 6,250 is before is equal to 625 plus 3,000 v afterwards. We can then put v by itself to say it's going to be 5,625 because it's 6,250 minus 625 is equal to 3,000 v. So therefore v is equal to 5,625 divided by 3,000, which equals 1.9 meters per second, which if you look at the values in the question is a sensible estimation. So let's now have a look at some questions concerning waves. So the first question says, there are different types of electromagnetic wave. Which type of electromagnetic wave has the shortest wavelength? And a new technology has been developed to charge small electrical devices from radio waves in the air around us. Explain how radio waves could charge a small electrical device. So pause the video now, then unpause the video when you want to go through your answer. Right, this is just a fact you've got to learn. The wavelength with the shortest wavelength in the electromagnetic spectrum is gamma. So you've got to be able to remember all the electromagnetic waves in order of wavelength and of frequency. Now, how does a radio wave work, and how does it be absorbed, and how does it be emitted by devices? You've got to learn that a small device can absorb a radio wave, but when it does that, it will create an alternating current in the device of the same frequency as the radio wave. And remember, for it to produce a radio wave, it's got to have it's got to have an alternating current, and that frequency of alternating current produces a radio wave of the same frequency. The next question says, figure 9 shows the wavefronts of a light wave passing through air into a glass block. Complete figure 9 to show the wavefronts as they pass out into the air. So pause the video now, then unpause the video when you want to go through your answer. Right, what you've got to show is when they're coming back out, they're back into air again. So it's going to be at the same speed. So it's telling us that it's going to be back at the same angle as it was previously. So the direction of the wave is parallel to the wave entering the block in a continuous line at the same distance apart as when they entered the block, because it's back to the same speed, so the wavelength is spaced back out again. The next question says, explain why there is refraction at the boundary between air and glass. So pause the video now, then unpause the video when you want to go through your answer. Right, so you've got to explain what is happening at refraction. So you've got to understand that refraction is due to the wave changing speed when it moves from materials of different density. So because glass is denser than air, the wavefront will slow down when it hits glass. But as you'll see in the diagram, you will get this refraction effect when the wave doesn't slow down at all the same time. So because some of the wavefront hits the glass before the rest of the wavefront, that will slow down before the other parts of the wavefront, and therefore one edge slows down before the rest, so the wave will change direction. The next question said the period of a wave in a ripple tank was measured. The period of the wave was 420 milliseconds and the speed of the wave was 0.6 meters per second. Calculate the wavelength of the wave. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this question? Well, again, it's a 5-mark question, so you're going to need a couple of equations here. Now, you're given the period, you've got the speed, and we want to work out wavelength. Now, we should know that wavelength speed is equal to frequency times by wavelength, so therefore, we can work out our value of wavelength from the speed and from the frequency and the wavelength. Sorry, from the frequency and the speed, my apologies. But we're not actually given the frequency in the question, we're given the time period. So what we've got to do first is convert our time period into a frequency. Now we know that frequency is 1 over time period. So we say frequency is 1 over 0.42, which is 2.38. We can then say that speed is equal to frequency times by wavelength, and we sub our numbers into the equation. So it's 0.6 is equal to 2.38 times by the wavelength. We can then rearrange it and make wavelength the subject to say 0.60 over 2.38, which is equal to 0.25 meters. The next question says that the electromagnetic spectrum is made up of waves of different wavelengths and frequencies. Give the type of electromagnetic wave with the lowest frequency. Then a wave has a wavelength of 2.5 kilometers and a velocity of 300 million meters per second. Calculate the frequency of the wave. So pause the video now, then unpause the video when you want to go through your answer. Like mentioned before, you need to know the order of electromagnetic waves in order of frequency and of wavelength. So the lowest frequency electromagnetic wave is radio waves. Then the next thing you've got to do is use our equation speed is equal to frequency times by wavelength. But when you check the units, meters per second is okay, but we don't work in kilometers in physics, we work in meters. So you've got to convert from 2.5 kilometers into meters. So 2.5 kilometers equals 2,500 meters. So it's 300 million meters per second equals frequency times by 2,500 meters. We rearrange to make frequency the subject, so it's 300 million divided by 2,500 is equal to 120,000 hertz. The next question says, figure 4 shows the equipment that's used to investigate the emission of infrared radiation from different colours of surface. The 4 hollow metal cubes are each painted a different colour. The cubes can be filled with hot water before the lid is put on. Describe a method to investigate which colour of the surface emits infrared radiation at the greatest rate. So pause the video now, then unpause the video when you want to go through your answer. Right, so for this one, you've got to think about what measurements you're going to take, what controls you're going to take to get valid results. So the first thing you're going to do is you're going to take the reading of the temperature using the infrared detector, and you're going to do it for each cube, and you're going to measure the different temperatures of the different cubes. But what has to be kept the same to get accurate and valid results? Well, all the cubes have to be the same volume, made of the same material, the same metal, because we are looking at the colour, not the material type, have the same volume of hot water added to it at the same temperature, and have the infrared thermometer the same distance away from the surface, and you'd want to have the same thickness of paint you use, and also leave it for the same amount of time before you take the measurements. Now you only got to take the measurement once to see how it changes, so you could do it after 5 minutes. Let's now have a look at some questions to do with magnetism and electromagnetism. So the first question says, when a conductor carrying a current is placed in the magnetic field, a force is exerted on the conductor. This is called the motor effect. Describe how the direction of the force can be determined using Fleming's left-hand rule. So pause the video now, then unpause the video when you want to go through your answer. Right, this here is just asking you to explain what Fleming's left-hand rule is. So the first thing you say is with your left hand, you will place your thumb and your first 2 fingers all at right angles to each other, all perpendicular to each other. Now your first finger indicates the direction of the magnetic field, your second finger indicates the direction of the current flow from plus to minus, and your thumb shows the direction of the magnetic force or the magnetic field or the motion of the object in that particular situation. You've just got to learn what they all are. The next question says, figure 8 shows apparatus to demonstrate the motor effect. The piece of wire is fixed so that it cannot move. This is the method used. Place the pair of magnets in their holder on the balance. Set the reading on the balance to 0. Pass a current through the wire. Record the new reading on the balance. When there is a current in the wire, the reading on the balance increases. Explain in terms of forces why the reading increases. So pause the video now, then unpause the video when you want to go through your answer. Right, this is all about what the magnetic force is going to be on the object, but it's very important to note that what's actually happening. Well, when you actually place a current through the wire is going to become an electromagnet. That's the principle of electromagnetism. When a current goes through a conductor, that conductor becomes an electromagnet, has a magnetic field around it that will interact with the magnetic field of the permanent magnets in the holders. That will cause a downwards force on the magnets in the holders, which is what is being measured by the balance. So at that point, the value on the balance will increase because the resultant force pushing downwards on the balance increases, because you've not only got its weight, but you've also got this new magnetic force acting on it. The next question says, in one experiment, the teacher determined that the force on the wire was 2.14 millinewtons. The current in the wire is 0.32 amps, and the length of wire within the magnetic field was 0.048 meters. Calculate the magnetic flux density between the 2 magnets. Give your answer to 2 significant figures. So pause the video now, then unpause the video when you want to go through your answer. Right, if you look on your physics equation sheet, you'll see that force is equal to magnetic flux density B times by the current I times by the length of the wire in the field L. Now we've got L, we've got I, and we've got F, and so therefore we can work out B. But remember, with F it's in millinewtons, so you have to convert that into newtons by timesing by 10 to the minus 3, dividing by 1000. So we can just put the numbers into the equation. So we say 0.00214 equals B times by 0.32 times by 0.048. We then rearrange it to make B the subject. So B is equal to 0.00214 divided by 0.32 times by 0.048. Therefore, we get an answer of 0.1393. But it says in the question to give it to 2 significant figures. So the first significant figure is 1, because the first 0 doesn't count, because the first significant figure is the first non-zero number. Therefore, 3 is the second significant figure, and then 9 is the third. So that will then cause the second significant figure to be rounded upwards. So when we go to 2 sig figs, so it's 0.14 Teslas. The next question says, figure 9 shows a simple motor. The force on the side of the coil of the wire labelled AB is 0.102 newtons. The current in the motor is 6 amps. The length of the side of the coil labelled AB in the magnetic field is 85 centimeters. Calculate the magnetic flux, the density of the magnetic field between the magnets and give the unit. So pause the video now, then unpause the video when you want to go through your answers. Right, once again we've got to use our equation F is equal to BIL. So we can make B the subject and we can work it out by saying, well, L is 0.80 850 meters, because we don't work in centimeters in physics, we work in meters. So L is equal to 0.850. So we say 0.102 is equal to B times by 6 times by 0.850. We then rearrange it and make B the subject. B is equal to 0.102 divided by 6 times by 0.850. Therefore our answer is B is equal to 0.0200. And what's the units of magnetic flux density? It is equal to the Tesla. The next question says, the direction of the force on the side of the coil of wire AB changes as the coil rotates. Explain why. Then explain what would happen to the coil if the commutator is removed and the coil is connected directly to the wires of the circuit. So pause the video now, then unpause the video when you want to go through your answers. Right. So how do you answer this particular question? Well, you've just got to explain what is going on as the coil rotates. So you would say the direction of the force depends on the direction of the current. That's from Fleming's left-hand rule. And also the fact that the magnetic force is produced by the current going through the conductor. So if the current's in the other direction, well, the force is going to be the opposite direction as well. Now the commutator, you've got to know the role of the commutator, reverses the direction of the current through the coil every half a rotation, so therefore the direction of the force will change every half a rotation when the commutator reverses the direction of the current at that time. Now you've got to think about what would happen if you didn't have your commutator doing that. Well, therefore if you didn't have your commutator changing the direction of the current every half a rotation, well then the current would only be flowing in one direction, so therefore it would rotate 90 degrees and then it would stop, because the magnetic field of the permanent magnet and the magnetic field of the electromagnet would be attracting each other. The wire would no longer want to move because it's attracted to the side of the permanent magnet, so it would only rotate for that short amount. So I hope you've enjoyed this particular revision session. If you've been successful and you've learned in today's revision session, you should be able to answer GCSE Physics examination questions for Combined Science Paper 2. You can assess your own understanding on GCSE Physics for Combined Science Paper 2, and you understand what topics you need to improve upon for GCSE Combined Science Paper 2. So thank you very much for watching this particular revision session for GCSE Combined Science Physics Paper 2. Have a lovely day.